Good morning, everybody. This lesson is going to be on how to draw and analyze a potential energy diagram, which kind of takes you through the step-by-step process of a chemical reaction. We're going to spend a couple of days worth of time on this because I'll introduce it and you'll do a little bit of practice today, and then I am going to give you additional practice with it for another session. You really just have to memorize how to work this. I will explain it in this lesson, and then I'm going to also film a video of me solving one of the worksheets that's in OneNote that you have, so you can work through problems as I talk through them, and then I'll let you work on some on your own. And that will take us through the first half of this kinetics and equilibrium chapter. So when a chemical reaction takes place, it's usually not a one-step process, it's a multi-step process. So we call that the reaction mechanism. It's kind of like the, step 1, step 2, step 3. When you're going through these step-by-step processes, some of them are fast and some of the steps are slow. The slow step is the one that determines the rate. So if you've ever run like a relay race, the slowest person on your relay team is really the one that's going to determine if you're going to win or not, because they kind of limit the speed at which the whole team is able to travel. The same thing here. The slow step is going to limit the rate of the reaction. The way that we show this kind of step-by-step process of a reaction is with a potential energy diagram. There's the way that the diagram is going to work. It's going to be a graph where the time is going to be on the x-axis, or reaction progress, sometimes they'll call it, and energy is going to be on the y-axis. And there's going to be points along the way that you're going to need to be able to identify. When we did matter and energy, we talked about heating curves. When you're going through phase changes, right, you have solids, liquids, gases, we have melting, we have boiling in between. With a potential energy diagram, it's going to be a curve. It looks like a roller coaster hill. So this is an entire potential energy diagram. You will not have these molecule pictures on it. It would just be blank, but I'll explain what these molecule pictures are as I go through the parts of the diagram. So when you look at this diagram, the way that I have it labeled, I have reactants on the left and products on the right, because if you are talking about a chemical reaction, the reactants are on your left of the arrow, and they make products. So we're going to read this from left to right. Now what you can also see with energy on the y-axis is that in this diagram, the reactants have more energy and the products have less energy. So overall, energy is being released. So what kind of reaction do we have if the reaction results in a release of energy? It would be exothermic. So this diagram is a diagram for an exothermic reaction where the products have less energy than the reactants do. And back to the prior lesson when we talked about delta H, the delta H is calculated by doing the energy of the products minus the energy of the reactants. So if we put numbers with this, if we say the reactants started with 10 and the products ended with 3, and we plug numbers into this delta H calculation and said 3 minus 10, the delta H would be -7. And if we have a negative delta H value, that also corresponds to an exothermic reaction. So this all ties together, okay? The diagram, the equations, the reference table. So I'm going to take you through different intervals on this graph and what they mean and what you need to be able to do. So this reaction is starting out with 2 white molecules and 1 G2 molecule, say green 2. And by the end of it, here's our products. We're going to have 2 molecules of W2G. I'm making this up, right? 2 whites, 1 green per molecule. It's not just a one-stop shop. You have to have the molecules get close to each other, and then they kind of make an in-between type of thing, and then they turn into these products. So on this, I'm going to show you the different parts you'll have to be able to label. So the first thing is where I'm starting my reaction. I'm going to throw some numbers in here just to make it kind of more real. I'm going to use different numbers than I did in this little delta H example. I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this first interval here where I'm starting my reaction, this is the heat of the reactants. That's the amount of energy the reactants have. So in this graph, the heat of the reactants is 4 kilojoules. I'm just reading the y coordinate. That amount of energy isn't enough to get these elements, or to get these molecules to react with each other. Okay, because remember, for a successful reaction to take place, the molecules need to have sufficient energy and collide at proper orientation. So at 4 kilojoules, that's not enough energy for them to do anything. They're just kind of bouncing off each other like, hey, nice to see you, get out of my way, social distancing, we got to keep away 6 feet. But if I start to add energy to this system by, let's say, just heating them up, those molecules will start to collide at a greater, with a greater amount of energy, forceful collisions. There's a better chance now that they will be able to collide successfully. Now, that amount of energy that needs to be supplied from where it started, so I'm not starting at the base, I'm starting where the reactants started at 4, but that extra amount of energy that needs to be supplied to get them to hit the crest of that graph, this is called the activation energy. Okay, so the activation energy is energy needed to result in a successful collision. So in this graph, if I'm starting at 4 kilojoules and I'm topping out at 8 kilojoules, the activation energy would be an additional 4 kilojoules. So again, the way that I figured that out was the top of the hill minus where I started. Okay, so that's the amount of energy that had to be added to get them to do something. Once those molecules have hit the crest of that hill, there's a transition that starts to occur. So when those molecules are colliding successfully and they start to actually transition, so we're going from the base all the way to the top, this is called the activated complex. The activated complex is kind of like the in-between. If you think of it like cooking, like if I'm making a cake, the energy that my ingredients have when I first mix them together in the mixing bowl would be like my starting point. That's not enough energy for me to get a cake. So I have to add extra energy, so I put it in the oven. As those ingredients start to gain energy, they start to react. So I don't have a cake yet. I don't have a cake yet. I don't have a cake yet. But when they get to the top, that's when they start to cook. That's when they have enough energy for the food molecules, the carbohydrates, the lipids, the proteins, to start to actually do something. I actually like that analogy. I've never used that before. Go me, yay! So the activated complex here would be the total amount of energy in the system at the highest point. So it would be 8 kilojoules. So it's like a transition state. So it's no longer reactants, it's no longer products, it's just kind of the in-between. It's like when the cake mix starts to bake, but we're not quite there yet. Once that transition state is reached, it's kind of like a roller coaster. Once you get to the top of the roller coaster hill, you can't get out anymore. You just have to let gravity do its thing. So that's what this kind of downward slope is. We finish transitioning, and our products are made. And the amount of energy that the products have is just this little interval here. So in this graph, this would be the heat of the products. And that would be 2 kilojoules. Okay? So we had a starting, is it like a pointer? No, that's just going to move things. So we have we have a starting point where the reactants are starting out with a certain quantity of energy. We obtain more energy through the activation energy. We reach this transition point of an activated complex, and then we scream as we go down the hill, and we end with a certain amount of energy that our products have. The difference between the starting point and the ending point, the difference between our products and our reactants, is our heat of reaction. So don't confuse heat of reactants and heat of reaction. So the heat of reaction, that's our delta H, and that's equal to the heat of products minus the heat of reactants. So for this one, heat of products we said was 2, heat of reactants we said was 4. So our delta H is -2 kilojoules. The negative sign tells us that it's exothermic. So this reaction overall gives off energy. Yes, we had to gain energy to begin with to get it to do something, but then overall there's a net loss or releasing of energy. So that's the delta H. Look at this crazy diagram. So those are the parts you need to be able to identify. I'm going to go through some more examples with you. Okay, so these next slides are just kind of taking it step by step through the different pieces. So here's that's our activation energy. So that's the amount of energy needed to get reactants to react. Activated complex, that's our maximum. So these slides are just like piece by piece. There's our delta H. Here's the different, sections just kind of laid out for you in words. So this diagram is a Regents question. You will never have to label an entire diagram on a Regents question, but you'd have to know how to identify each of the individual pieces. So for this, interval 1, so interval 1 takes the difference between my starting and my ending point, so this would be my change. The delta H is never going to hit the top or the bottom of the graph. It's always going to be the difference between your starting flat part and your ending flat part. Now for this diagram, my products are ending with more energy than my reactants. So if there's an overall gain or absorption of energy, this would be an endothermic graph. And the delta H would have a positive value because I'm obtaining more energy overall. For number 2, that's just from the base to where my reactant starts. So that's the heat of my reactants. Interval 3 is from the base to where I'm ending my product. So that's the heat of my products. So interval 1 is just the difference between intervals 3 and 2. Interval 4, that's the hill that I have to climb. So I'm going on my roller coaster. I don't start at the ground. I start in the roller coaster car. So I'm starting here, and I have to climb this hill. The height of the hill, not the height from the bottom, but just the height of the hill that I have to climb, that's my activation energy. And I'm going to skip to number 6. 6 goes from the bottom all the way to the top. Now, interval 5 is not one that we've looked at in the prior graph, but let's think about what this could be. We're kind of starting where the products are, and we're climbing this hill going backwards. Some reactions can travel in opposite directions, so we can go from left to right, and we can go from right to left. So number 5 is a hill that I have to climb, but it's starting backwards. So this is a different activation energy. This is the activation energy of the reverse reaction. So I can climb back over the hill the other way. Now this is a shorter hill that I have to climb than the forward activation energy, but it's still an activation energy. Here's another example to work through. I just want to show you the different possible, scenarios that you're working with here. So here's 4 different pieces. So this reaction is A plus B react to make C plus D. First of all, what kind of reaction would this be? Would this be endothermic or exothermic based on just the, absorption or release? Are we gaining energy overall or are we losing energy overall? Since we're gaining energy overall, it's an endothermic graph. And that might be all you have to answer. It might just give you a graph and say, what kind of reaction is this? Sweet. Or you might be given a blank coordinate, and it might give you a starting point, and it might say, okay, draw a potential energy diagram for an exothermic reaction. Point. If it said endothermic reaction and it started here, point. You just have to show that there's a difference. Endo is gained, exo is lost. Okay, so looking at this graph, 1 is our starting point. So the amount of energy that we start with before we do anything, that's the heat of our reactants. Let's look at 4, because that one's easy. It's our ending point, right? It's the interval from the base to where we end. So that's the heat of our products. 3, anytime you have an interval that goes from the bottom all the way to the top, that's our activated complex. And now number 2, look at it, it's kind of hovering. It's not touching the top, it's not touching the bottom of the axis of our coordinate. It's touching where we start and where we end. Any interval that touches where you started and where you ended, that's going to be your delta H, your change in heat overall. So here's just 2 examples of endothermic and exothermic. So I already kind of talked about this. An exothermic reaction releases energy overall, so you end up with less energy in the products. An endothermic reaction absorbs more energy than it gives off, so you end up with more energy by the time you get to the products. Okay, first of all, these triangles shifted. They should be here. Okay, how do you determine if a reaction is exothermic or endothermic from an equation with the heat included, or using the value of, that should be delta H. Okay. If you are given an equation like this, or it might say, or heat, or it might say, plus 10 kilojoules. If it's on the left-hand side of our arrow, it's showing it's going into the reaction. It's an endothermic reaction. And the delta H would have a positive value. So that's what it looks like if energy's on the left. Look, there's more energy on the left of this graph than there is on the right-hand side. If the heat is on the product side, we always add it. We don't subtract it. So it's being added to the products. So again, it might say heat. It might say plus 10 kilojoules, whatever. But if it's on the right-hand side of that reaction arrow, it's an exothermic reaction, and there's going to be a release of energy overall. So this would be the graph for it. There's more energy change on the right-hand side of the graph than there is on the left-hand side of the graph. Okay? So if energy is on the right, there's going to be a bulk change on the right. If energy is on the left, the bulk of the change is going to be on the left of your graph. Okay, so that's just something you have to memorize. So here's an example with a chemical reaction. I took this reaction right off of the reference table. This is one of the ones on reference table I. So what would this energy diagram look like? So we have a process and we have energy on the right-hand side. Well, if we have energy on the right-hand side, that means the bulk of our energy has to be on the right-hand side. So that would be exothermic. That should be flat, but you know what I mean. So an exothermic reaction if energy is on the right. So there's more energy given off than there is taken in. The last thing I want to show you with one of these graphs, and I know this is long, but this is just getting through all this information. If you add a catalyst, so a catalyst will speed up a reaction. So the reason it speeds up a reaction is because it decreases activation energy and it provides an alternate reaction pathway. You learned about catalysts in living environment. An enzyme is a biological catalyst, right? An enzyme helps to speed up reactions in your body. It doesn't change the amount of heat. Nothing will change this, and it will not change this, okay? So the delta H is not going to change. This is a constant value. But let's pretend this is a mountain, and I want to get from this left side of the mountain to the right side of the mountain, okay? One path I could take is to climb the mountain, climb all the way over the mountain to get to the other side. Okay, and that's going to take me a certain amount of time. If I want to get there faster, I can drill a tunnel through the mountain. Okay, drilling a tunnel through the mountain gives me an alternate pathway that required less of an energy input for me. Okay, if I have to climb all the way to the top of this mountain, I have to put in this amount of activation energy to get to the top. That's a normal pathway. But if I drill a tunnel through the mountain, instead of having to climb all the way to the top, I only have to climb to this height. So this hill, this shorter hill that I have to climb to reach my new crest, that's the activation energy when a catalyst is added. Okay? So it's less activation energy than I need. If you are given a graph and you're asked to alter the diagram to show what it would look like if a catalyst was added, that's all you have to do. Just make a shorter hill. You're not cutting straight across. Do not cut straight across. Okay, that's not what a catalyst does. You always need some sort of energy to get the reaction going. Okay, this making a flat line is saying you don't. You always need a little bit of energy. But what a catalyst does is it just decreases the total amount that has to be added. So you just put a dotted line in there. So here's a couple examples of graphs, like if a catalyst was added to the reaction, which intervals would change. So let's just draw in a catalyst. Here's my catalyst. Well, what would change? Anything that would have originally touched the top of my graph is now going to have a new top. It's going to have a top where the catalyst is. So interval A would change, and interval C would change. B is not going to change because my amount of energy I start with didn't change. The amount of energy my products have doesn't change. It's just the height of the hill in between. So same thing for the second graph. If I add a catalyst, instead of having to go all the way to the top to reach this total activation energy, well, now I only have to go this high, so this would change. My activated complex would change. And this is the activation energy of my reverse reaction. That would also change. Draw an energy diagram for an endothermic reaction and indicate with a dashed line what it would look like if a catalyst were added. Okay, so endothermic. Endo, absorb. So that means we have to go uphill more than we go downhill. Uphill more than we go downhill. And now we add a catalyst. Just shorten that hill a little bit. That's all you have to do. And then this last thing, how do you draw an energy diagram for a reaction using table I? Draw the energy diagram for a reaction producing 2 moles of NO2. So you would go to reference table I and you would find the reaction that makes NO2. So this is it. And then the delta H on the reference table is positive 66.4 kilojoules. Positive number, and it shows you this on table I at the bottom. It tells you a negative sign is exothermic, so a positive sign is endothermic. Endo means absorb. I put more energy in than I get out. That's all you'd have to do. You just refer to it. So that gives you an overview of potential energy diagrams. The next video will be me working through one of the worksheets that's in OneNote. I think it's the easy PE diagram one. So stay tuned for that one. That will help you work through the first one. And then the second one will be more of a challenge. Thanks, bye.